All right, welcome everyone. This is 219 differential equation course. I mute you all, but if you want to talk, you can unmute yourself and ask your questions. Well, this is our syllabus. Let's go over the syllabus first. All right, well, here is my name, Özcan Yazıcı. I am a member at the math department, faculty member. And our course assistant is Tunahan Yılmaz, and his office is at Zifrit, and my office is at M217, 217 at Math Building. One, two, seven, and office hours are Tuesday, 2:30 to 4:30. So during this time, I will be in my office. You can come and ask your questions. You can also attend office hours through Zoom link. I will also open the Zoom link during my office hours. So if you have any question about the course, you can come and ask your questions, okay? All right. Well, here is the website of the course. We make some announcements through this website, but from now on, you should follow ODTÜ class for the announcements. We will do most of the announcements to ODTÜ class here, okay? You can find the updated syllabus there. And this is our textbook, Boyce and Prima. It's good to have one to do some exercises. Well, on the course website, there are suggested exercises, so you can go ahead and try to those problems from the book. As for the attendance, I will not take any attendance, but of course you should follow the course. You should come to each lecture, okay? But this is not a must, I would say. No attendance will be taken in the course, but you should definitely come to the lectures to get a good grade. Well, let's talk about the grading. We have 2 midterms and 1 final exam. So we are planning to do this midterms in class midterms. Well, these are the dates. 30% each midterm, and we have 40% for the final. Total it is 100%. No quizzes, no recitations. This is only 4 hours course, okay? So we will meet on Tuesday and Friday, right? All right. Well, let's go to our web page here. You can Google it. for the web page. Oops, not this one. By the way, I'm taking recording, and this I will put on ODT class after each lecture. You will able to see the lecture video recordings, and I will also put the lecture notes on ODT class. All right, so this is our web page. Well, there is here, for instance, you can find suggested problems, a number here, the 4th, 9th edition and 10th edition. There is also 10th edition of this book. Okay, so you can check this. So these are important because this will help in the exams. Okay, there are many exercises here. Well, there is one question. Am I going to upload the video on YouTube? I guess it will automatically upload it to YouTube. And also I will put a link to the ODT class, so you can also go ahead and watch from ODT class. There will be a Zoom link, okay, in the ODT class for the videos. All right, well, there is here past exam questions. You can see some examples of the last year's exams. Here you can see the syllabus. Well, for syllabus, maybe it's better to go with it doesn't open. Well, I guess it's about the iPad, because I did this earlier with the computer. Anyway, you can also find the syllabus on ODT class. All right, what else we have here? Yeah, that's it, I guess, yeah. Well, our makeup policies, you will need an acceptable excuse like a report, medical report, or something similar to take a makeup exam. I don't suggest makeup exam, but if you have to take it, then you can take it with some report. You can only take one makeup exam. Be careful with that. Okay, so you cannot take 2 makeup exam for 2 midterms, or 1 midterm, 1 final. It's not allowed. Okay, so you can take only one. And this makeup exam will be after the final. We will do announcements for this. Here is the NA policy. If you miss 2 midterms, you will get an NA. If you miss 1 midterm and your other midterm is less than 15 over 100, then you will get NA again. If you take 2 midterms again, two midterms and your total is less than 30 points, then you will get NA. Okay, so this is clear in the syllabus. All right. Here we have the links for the Zoom meeting, and I guess the updated syllabus has also YouTube links on ODT class. This is the older version. And we just talk about office hours. Office hours are on, again, they're on Tuesday from 2:30 to 4:30. Tuesday, 2:30 to 4:30. Let's go here. Not this one. Well, here is the course schedule. We have a detailed schedule for each week. We will follow this schedule. So for instance, today we're gonna do 1, 1, 2, 2, and 2, 1. Okay. Sorry, 1, 1, and 2, 2. And on Friday, we will do 2.1 linear equation, integrating factors, and so on. So in this course, we will learn how to solve differential equations. Of course, we cannot solve all types of differential equations. We can only solve in certain type differential equations, and we will focus on this, okay? All right, before we start, do you have any question? Okay, there's one question. Some of the suggested problems do not have the solution key. Is there a way to learn those? Well, I don't have any information about that. What you can do is, if there is no solution key, you can come and ask me during the office hours. You can do that.
Do you have a suggested way to study this course?
Suggested what?
Suggested way to study this course.
Suggested way is like try to solve this exercises from the book. That will help a lot, because differential equation is about solving differential equations. So you need to practice more and more. And we have here suggested problems on the web page. You can go ahead and try to solve after each lecture. Try to solve these problems. This will help a lot. Okay, so because in the exams you will see similar questions, so that will help. Then that will be enough. All right. And of course, if you cannot solve the problems here, you can ask me. You can come to my office hours. You can go to your course assistant, Tunahan, and ask him, okay? All right. Any other question? Any other comment? Well, during the lecture, you can stop me and ask any questions you want, okay? Anytime you can unmute yourself and ask your questions. Okay. Now let's start with the basics of differential equations. Now this is Maths 219. Spring semester. All right.
Hocam 2023 olacaktı galiba.
Right. Well, sometimes people call it spring 2022 and 23. So let's look at. All right. Let's start with the introduction. So we will define what a differential equation is. This is 1.1 in the book. Okay, the definition. What is a differential equation? Well, you already took calculus 1 and 2, and in the calculus, most of the time you are given a function and you do some work with the function. You find a derivative, you integrate, or you are given a curve and you find the area, blah, blah, right? So you are given explicitly something and you do something with that given function. In this course, we will do kind of the reverse. So we are not given the function, we are given an equation, which is called the differential equation, and we will try to find the function which defines this equation, okay? So a differential equation is this. A differential equation is an equation involving one or more derivatives, is an equation involving one or more derivatives of an unknown function. Okay, so unknown function is like, we will call it like y, and it's a function of x, t, whatever you call it. Okay. Well, this is our first definition. So we will do some examples later. Let's give these definitions. First, the highest derivative in the differential equation is called the order of the differential equation. The highest derivative in a differential equation is called the order of the differential equation. Okay. Another definition. So let's say you have, for instance, in the differential equation, you have the highest order is like 3. You have a derivative of order 3 in the differential equation. Then you say this differential equation is of order 3. And a differential equation is called ordinary differential equation if there is only one independent variable. A differential equation is called an ordinary differential equation. Okay. For short, we will write ODE. Okay. ODE. If there is only one independent variable. That means what? Independent variable is like, for instance, you have, let's say, y is equal to y of x. Okay. It's a function. Y is called dependent variable. X is called independent variable. Okay. Y is dependent variable, and there is only one independent variable here, which is x. X is the only one independent variable. Well, if you have, for instance, y is equal to y xt, then there are now two variables, two independent variables, x and t. X, t are two independent. Of course, these are not differential equations. These are simply the functions, okay? So here we define what's a dependent and independent variable. Xt are two independent variables, okay? So if there is only one dependent variable, then you say it's an ODE, ordinary differential equations. If there are more than one independent variables, then you say it's a partial differential equations. Let's also write this. If there are more than one independent variables, then differential equation is called partial differential equations. Partial differential equation.
Quick question. Is there a
And
great
in this case, we write PDE for short. Well, this partial comes from partial derivatives. Remember, if you have two variables in calculus, then the derivative, you can take the derivative with respect to x and y, and these are called partial derivatives, right? So if your equation is in terms of partial derivatives, then you say it's a partial differential equations, PDE. Any questions so far? Let's
this
do
go-
some examples.
this is gonna be a weird question, but is there any sort of gray area between ODEs and PDE?
Well, let's start with the simple one. dy dt, that means the derivative of y with respect to t. So y is a function of t is equal to y minus sine of t. Okay, there is, well, I couldn't hear you. Can you ask me again? There is one question, I guess. Someone has a question?
I did. I texted in the chat now.
Okay, is there a differential equation that is neither? No, well, by definition, OD or PD, it must be either PD or OD. Okay. Well, the thing is, if it's a PDE, it cannot be OD. Okay.
Okay.
Right. Good. So there is no equation which is neither PD or nor OD. It must be either an ordinary differential equation or partial differential equation. Well, let's look at this one. this equation is a differential equation because we have a derivative here. Y is the dependent variable, t is the independent variable, and there is only one independent variable, which is t. So it's an ordinary differential equation, and the order of this differential equation is 1 because we have only one derivative, right? Here, this is basically y prime of t, right? So this gives the order, and there is only one variable. T is independent variable. So that means basically this is an ODE of order 1. Okay. Well, let's do another example. Let's look at this equation. The second derivative of y with respect to, sometimes we call independent variable tx, depends on the examples, okay? So we can change the independent variable and we give different letters for the independent variable. Derivative of y with respect to x, second derivative of y plus dy dx to the 219 plus cosine x is equal to 0. Well, there is again one independent variable, which is x, okay? And it's a second order now, right? So here, this is the independent variable, and dependent variable is y, and we take the second derivative, so this is order 2. So this is an ODE of order 2, okay? Another example, let's take this equation, phi xx. That means that we take the partial derivative with respect to x plus cosine cube x phi xy square is equal to ln xy. Is it an ODE or PDE now? Well, now we have two variables, x and y. They are independent variables, and phi is the dependent variable, right? We have some answer here. Okay, what does this sign mean? I guess you're asking about this. So here, phi is a function. Phi is a function like this. It depends on x and y, okay? It's a function. And this represents the partial derivatives, okay? Partial derivative means you keep y constant and differentiate with respect to x. But don't worry about this. We will not deal with PDE, partial differential equations, until the end of course, okay? In the last 2 weeks or 1 week, we will do some PDE, but other than that, we will mostly deal with ordinary differential equations, but it's good to know what is a PDE. So this is a PDE, partial differential equations because there are two independent variables, okay? Here, x and y. These are two independent variables. That means it's not an ODE anymore, okay? It's a PD. What is the order? Well, here you see we differentiate twice with respect to x. And also we differentiate twice here, okay? So the largest derivative, largest order of the derivative gives the order of the equation. So it's a PD of order 2. Okay. Any question? All right. Well, let's talk about some notations. These are common notations for the derivative. Well, for the nth derivative of order n, we use this. Or this. Here, y is a function of x. Okay. Oh, okay. There is one question. Why does this a PD, partial differential equations? The reason is we have partial derivatives. Okay. Phi x means you differentiate phi here with respect to x. That means we have partial derivative. We keep y constant here. To find this, we keep y constant and we differentiate with respect to x. So we have partial derivative. That's why it's called partial differential equations, PD. Okay, is it clear now?
To be honest, I wasn't able to understand because they are both independent variables, right?
Oh, well, there is a dependent variable here as well. I didn't say, but this is dependent.
Okay, this one is dependent, but we're taking derivative according to x twice.
Yes.
And we are doing this derivative according to independent variable.
Right.
Therefore, I wasn't able to understand why it is partial and like.
Because, okay, let me give an example. Let's say phi is well, basically, if you have two variables, more than one variable, it's called PD, partial differential equation. This is the definition. If you have more than one independent variables, then it's a partial differential equation. And here we have two variables, independent variables, x and y, okay? That's why it's PD. Well, let me clarify this with an example. Let's say phi is, for instance, sine x times y. Okay, it's a function of x and y. So what is phi sub x? So what you do is to find phi sub x, you consider like y is a constant, so it becomes like cosine x times y times, you consider y is a constant, so it becomes times y, chain rule, right? So we differentiate with respect to x. When you differentiate with respect to x, that means we're talking about partial derivatives, okay? So it's a partial derivative. And when you have a partial derivative in the equation, it's called PD. Clear now?
Okay. Yeah, thank you. Now it makes sense.
All right. So basically, if you have more than one variable, then more than one independent variable, then it's called PD. Well, don't worry about this. We will do many examples during the course, and you will get a better idea what's an ODE, what's an order, and so on. Well, we also have this linear ODE. Let's also talk about this. another definition. That stands for definition, by the way. I will use a lot in the course. A differential equation is called a linear ODE of order n. Order n means we differentiate n many times, right? What is linear means here? What does linear means here? Well, it means the following. If it's of the form, if it is in this form, we have a function of x. X is the independent variable, and y is the dependent variable. So this here, y to the n, that means nth order differential equations, okay? Plus another function. So a n x is a function. It's a function of x. These are called coefficients of the differential equation. Another function of x, and we have y, derivative of y of order n minus 1. And you go like this. A1 x y prime plus A0 x y is equal to another function. Let's call it f of x. So if you have a differential equation in this form, it's called linear differential equation. It's an ODE because there is only one independent variable. Let me maybe call this here. X is the independent variable. Y is the dependent variable. Dependent variable. Okay, n is the order. What are this? These are functions. These are coefficients, okay? Coefficients. Coefficient functions, let's say. So they are the functions of x, like, for instance, an minus 1 can be like x squared times cosine x. Any function of x, okay? Let's give some examples.
Hocam, is this valid in case n is not 0?
Well, if n is equal to 0, we don't have an ODE. Maybe I should say here n is a natural number. But if n is equal to 0, we don't have a differential equation. That means we don't differentiate, right? It's an equation. It's an usual equation, what you know from high school, okay? Well, there is one question, the coefficients different than 1. This is linear, right? It doesn't depend on the coefficients. The only thing we require with the coefficient, they must be a function of x. If the coefficient doesn't depend on y, then it's a linear equation, okay? So this is the definition of linear ODE. The coefficients can be different from 1 and it's still linear, okay? Let's give some examples. Okay, let's look at this one. 2x squared y double prime plus y prime minus sine x times y is equal to x squared tangent x. Well, is this a linear ODE. It's an ODE for sure because there is only one independent variable. But is it a linear ODE? What do you say? Does it look like the form here given by this? We have this form here. Does it look like this one? Well, there are answers no, yes, linear right thing, not really, and doesn't have consistency. What is consistency? Okay, Tuba says yes. Well, it's linear. Let's go back to the form here. We have the coefficients. They are the functions of x. So these are functions of x, functions of the independent variable. Okay, the coefficients. And see this here. This is a2, for instance. It's a function of x. The next one is, this is 1 times y prime 1. That means a1 is the constant function. You can think of this as a constant function of x again. Okay, it's a constant function. This is a1. This here is a0 x, okay? And this is my f of x. So you see here, it's exactly in the form of a linear ODE. So it's a linear ODE of order 2. Is a linear ODE of order 2. Okay. So there's one question. Can we assume that a2, a1, a0 can be any function, any coefficient? Yes, they can be any function, but they must be a function of x, not a function of y. I will give an example now, which is not, maybe let's give this example. Y triple third derivative of y plus x times y prime, y double prime plus y times y prime is equal to 0. Well, is this a linear ODE? No, it's not. Good. We have many answers here. The reason is the coefficient of y prime, right? A3 here, it depends on y. So it must be free of phi. So it's not a linear ODE. Okay, so because of this term, okay, not a linear. It's an ordinary differential equation. It's an ODE. It's an ODE of order 3, but it's not linear. Okay. Okay, there is one question. Can we assume that A2's order doesn't have to be? No, we don't care about the order of A2. What's the order of A2, by the way? It's a function. We don't have an order for the function. If it's a polynomial, we can talk about its degree, but it doesn't have to be polynomial, the coefficients. So they are functions and we don't talk about the order of a function, okay?
Hocam bir şey sorabilir miyim?
Sor bakalım.
ODE dememiz için bir tane independent olması gerekmiyor muydu?
Right.
Bir A3 mesela 1, A2 X, A3'te Y olmuyor mu? Ya da
Well,
A1 diyelim. Ya
well,
AN X ve
not-
Y'yi
not
vazgeçmiyor
really.
mu?
Cannot say the coefficients are A1, A2, A3 here because it's not a linear differential equation. If it's a linear equation, then we call the coefficients are A1, A2, A3. It's here, what we say is X is the independent variable because we take the derivative of Y, not X, okay?
Mhm.
And Y is the independent variable. Right? There is only one independent variable. Sorry, Y is the dependent variable. Sorry. Y is the dependent variable, X is the independent variable. So there's only one independent variable. That's why it's ODE. Okay?
Okay hocam, teşekkürler.
Well, there's another question. In the first example, 1 in front of Y prime is dependent to X because of... yeah, you can think of like this. One constant function, you can think of constant function of any function of any variable, okay? The constant function, you can think of constant function, it's a function of X, function of Y, whatever, okay? It's free. You can take it as like as you want, okay? So you can say constant function is a function of X, that's fine. The thing is, the coefficient cannot depend on here. The important thing is the coefficient cannot depend on the dependent variable, okay? Here, the dependent variable is Y in this equation. Dependent variable is Y. So the coefficient cannot depend on Y, basically, for linear ODE, okay? Any other question? All right. Well, here we have some examples of differential equations. You can cook up your examples. You can write many examples like this. But the thing is, that doesn't mean that you can solve these equations. Solving equation is a totally different story, okay? Sometimes it looks like very easy, but it's incredibly hard to solve differential equations. So we need some certain type of differential equations to solve, to deal with. Okay, so we will
Hocam.
talk about, of course, this certain type of equations. Yes.
Bu son örnekte lineerliği bozan nedir?
Y olması şurada. Y ile çarpıyoruz ya.
Hı, tamam.
Yani mix termler olamaz. Y ile Y prime'i çarpamayız. Let me give another example. Then we will give a break. For instance, Y prime plus 2Y square is equal to X. Well, this is again not linear because we have Y square, okay? Because of the term Y square. it's like the coefficient of y is like y. You can write this like y times y. So the coefficient of y, it's not a function of x, it's a function of y. So it's not linear, okay? Right.
Hocam,
If you have a square of the derivative, it's not again linear. Another example.
but y is function of x.
Yes.
So this term is includes x only.
We don't think like that. Okay. I understand what you're saying. Y is like function of x,
Yes.
so like the coefficient is like function of x, but I mean, this is like the type of the equation. If you write explicitly, then, but we don't know what y is, right? That's the problem.
Okay.
If you know what y is, you replace y with that function and it becomes a linear OD, but we don't know what it is, okay? So we need to
Okay.
see explicitly the coefficients, okay? In terms of x.
Maybe y can be dependent on a second independent variable besides
second-
the x.
That's fine, but it's a linear PD, but we don't talk about this now, okay? It becomes a PD then. Now we're talking about ordinary differential equations, right? Well, if you have, for instance, y double prime plus y prime square, it's not linear again. So basically, you can think of this like all the derivatives appears in the differential equations without any mixed terms. You don't have any squares, cubes like y cube, y prime cube, or you don't have mixed terms like y times y prime or y primes times y double prime. So that's not it. Let me give one more example. Again, this is not linear because we have a mixed term. The coefficient of y prime is, it's not a function of x, it's given by y, okay? So is not linear. They're all ODE. It's an ODE of order 3, last example, but it's not linear, okay? So linear ODEs are important. Later we will talk about linear ODEs later. We will try to solve linear ODEs. We will have several methods to solve ODEs, linear ODEs. That's why it's good to know what's a linear ODE means, okay? All right, do you have any other question? I try to answer your questions from the chat, but if I miss something, you can ask now. Unmute yourself and ask.
So as long as the coefficient of y primes are somewhat linked, not linked, x dependent, even if it's like some random number like 2, 3, 5, whatever.
That's
It's
fine.
linear.
That's fine. Yeah, so the constant functions are okay. Because you can think of this, right? A2x is equal to 5. It's a, it is a constant function. That's fine.
Thanks.
But that is not allowed, right? A2x is equal to y squared. That doesn't make sense, okay?
That's y dependent. That doesn't count.
Right. All right, let's give a break now for 10 minutes. So let's meet at 11:50, okay?
Hocam mola kaça kadar dediniz acaba?
11.50'de devam edeceğiz.
Tamam, teşekkürler.
Hı hı.
Hocam ders kayıtlarını yükleyecek misiniz Octopus'a?
Yükleyeceğim. Ders kayıtlarını yükleyeceğim.
Hı.
Dersten sonra Multiclass'ta hem video hem lecture notları.
Tamam hocam, teşekkürler, sağ olun.
Rica ederim. All right, welcome back. So before we continue, do you have any question? All right. Well, now let's talk about direction fields. This is 1.3 in the book. Let's take a differential equation in the form. So take a differential equation. The dy dx is equal to f of xy. Okay. So here x and y are independent variables. Sorry, x is independent variable, y is a dependent variable. And we have here f of xy, it's a function of x and y. It can be linear or not linear. It's an ODE. Okay. Well, in this equation, the graph of the solution y is equal to y of x. So y is the solution, and its graph is called the solution curve. Solution curve. Okay. So what does it say, this equation here? We have derivative of y is equal to some function. Right-hand side gives this derivative, right? Derivative of y with respect to x at the point xy. And derivative, the geometric meaning of the derivative is basically, it's the tangent line, the slope of the tangent line at that point, right? So here, this f of xy tells you the slope of the tangent line to the solution curve at an arbitrary point, xy. So let's write this as a remark. F xy, it's a real number at the end, right? You give xy, so you find a real number, gives the slope of the tangent line to the curve, the solution curve, y is equal to yx at the point. The curve is in R2 in the plane, so we have two coordinates, x and y, at the point xy. So this is a nice fact because this will help to sketch the solution curve without finding explicit formula of the solution. So without finding the solution, we will be able to draw the solution, okay? Simply using this equation, differential equation. So how do you do that? Well, so this is our goal. the first call without solving equation. The ODE, we will sketch the solution curve. Solution curve y is equal to yx, okay? Maybe this is better so that you can follow. All right, well, okay, let's go back and do this. So let's do some examples. So let's sketch the direction field. Oh, well, maybe we should first talk about what is a direction field. Okay. Well, let's define what's the direction field first, then we will do some examples. Well, in the XY plane, to sketch the solution curve in the XY plane, we draw small line segments at each point, having a slope f of xy. We draw small lines at the point xy with slope equal to f of xy. And the curve following these lines are basically the solution curve, and the sketch is called the direction field, okay? This sketch is called direction field. Direction field. And the curve following this small line segments, it's called it's the solution curve. The curves. Solution is not unique, so we have many solution curves. We'll talk about this as well. So the curves following these lines are the solution curves. Okay. Okay, let's do one example with this. An easy one. Let's take this equation. Dy dx is equal to 2x. This is quite easy to solve, but we will not solve it now. Later we will solve it. Sketch the direction field. and solution curves. All right. Well, we work in the plane, so let's draw a plane like this. To draw the direction field, we take some arbitrary points. There is no rule how to choose these points. You can choose as many as you want. Okay, so let's take some points like this. These are like lattice points. So we have 1, 2, 3, for instance. Okay. So these are some points with integer coefficients, integer coordinates, -1, -2, -3, and so on. This is 0. All right, so let's try to sketch the direction field. Well, at each point, for instance, we are at this point, let's say, at 1. The x-coordinate is 1, and our function is, this is your f of xy. So the slope at this point is 2, okay? So 2 is like this. So you will draw a line with slope 2. It's like this one, okay? And maybe let's go to that point. Oh, wait. This is 1. This is with slope 1. And let's go to this point. This point is like, we have like slope. This is 2, right? It's 2, 2. So the function here, f of xy, it takes, right, this is slope 2, it's gonna be slope 4. It's gonna be more like this. It's like more vertical, right? Oh, this is x and y. And when you move right hand side, it's gonna be like more and more vertical. So for instance, at 3, it's like this. Okay. At 2, it's like this. Well, I know this is not a very good picture. They're all alike like this with the same x coordinate. Okay. At 1, maybe let's do it like this. Okay. So at 0, it is 0. Okay. Well, we cannot, okay, there is a question how accurate we should draw this. There is, you don't have to be too much accurate with this, okay? So just follow the, basic geometry, and it doesn't have to be perfect picture, I would say. So why do we choose 2, 2? We don't choose 2, 2 here. This is just an example, okay? we draw this line segments at each point. Okay, each points like this. Okay, 2 was just an example. Okay, maybe let's start this again. For instance, at 1, 0, the slope is what? F of 1, 0, which is 2. Okay. So it looks like this. 2 is like sound like this. Okay. At 2, 0, for instance, the slope is 4. F 2, 0, which is 4. So it's going to be like more vertical, like this. Okay. At 2, 0, at 2, 1, at 2, 2, they're same, right? They have the same slope because it doesn't depend on the y coordinate. So we have the same slope like this, like this, like this. Okay. Yeah. At 0, it is 0. That means we have a horizontal like this. And the slope is 0. So let's continue at 1. We have the same slope with 1, 1. So it's going to be they're parallel. Okay, like this. Okay. Well, at 3, it's going to be more vertical. It's going to be like more like this. Okay. And the similar happens on the left-hand side. -1, it's going to be, let's take a point, for instance. -1, 0. We have the slope. -2. Okay. -2 means something like that. Okay. At -2, 0, the slope is -4. So it's going to be more vertical, like this. Okay. So let's, okay, what about on the y-axis? Well, it's always like horizontal, because x is 0 here. So we have sort of a picture, right? So this is the direction field. Let's draw the solution curves. So what we have is like, okay. Let's follow, for instance, this path. Okay. So you see these lines are like tangent to this curve. Another curve is like this. It's not a good drawing, but it must be like maybe more like this. Okay. And you can draw another one like this. Okay. So these are solution curves, okay? Any question with this? Yeah, so when you go to infinity with x, right? So the slope will be infinity. That means it's going to be a vertical line. Yeah, and that makes sense because this. Now we will solve this, and you will see why this happens. Okay. So if you solve this equation, how do you solve this equation, by the way, this differential equation? How do you solve this? So there's one question, why do we have this horizontal lines at the origin? At the origin, x is equal to 0. Okay. On the y-axis, x is equal to 0, and f of xy is equal to 2x. 2 times 0 is 0. That means the slope is 0, so we have a horizontal tangent line, right? Well, right, so we integrate this. So we had dy dx is equal to 2x, and integrate both sides. Like this. Or maybe let's write like this. It's better. Oops. Okay, and now we get what? We get basically y is equal to x squared over 2 plus a constant. So you see here, x squared over 2 is a parabola, which looks like this here solution curves, right? And as x goes to infinity, right? So it's going to be like the tangent line will be more and more vertical. So it's going to be a vertical line at infinity. The c here is arbitrary. C is any constant. And you can also see here in the solution curves, when c is equal to 0, this is the solution curve, the first one. So this is when c is equal to 0. Here, this is when c is equal to 1. Okay, so you have many solutions. You have infinitely many solutions depending on the constant in the solution. It was an easy differential equation, so we could be able to solve it. This is not the case always. Okay, but still we can draw the direction field using the equation without solving. Okay, any question with this? All right, this is gonna be x squared, sorry. All right, thanks. Well, let's do another example. Here we consider this one. Y prime is equal to y times y minus 1. Okay. Well, first of all, this is not a linear ODE, but that's not the point here. Well, let's say this is my f of xy. So that means basically slope is given again right hand side, because this is the left, on the left hand side we have the derivative, and derivative gives the slope of the tangent line. So let's draw the sketch the direction field first. Maybe, well, this is not easy now. What I will do is I will do in a more systematic way here. So let's try to understand what happens with the slope. Okay, the slope is given by a function y times y minus 1. So let's make a table for this purpose, but we also want to know the concavity of the solution curve. So for this purpose, let's look at the second derivative. Remember, in calculus, to get some information about the concavity, we look at the second derivative, right? Concave up, concave down. If it is the second derivative is positive, it is concave up. If it is negative, it is concave down, and so on, right? For concavity, we check second derivative. Well, what we do is we differentiate this again. From here, we get what? We get basically the second derivative of y, differentiate with respect to x. We use the product rule, y prime times y minus 1 plus y times y minus y times y prime. Sorry. Well, let's write this everything in y. So replace y prime by y times y minus 1. So it becomes y times y minus 1 square, because y prime is equal to y times y minus 1, plus y times y minus 1, y square times y minus 1. Or you can take this in parentheses and it becomes y times y minus 1 parentheses. We have y minus 1 plus y, 2y minus 1. This. So for concavity, we will use this. Okay, there is one question. How do you obtain this? Well, you see y prime is given by this. So we replace y prime with this, okay? We replace y prime by right-hand side. All right, let's make a table now. We have y, or maybe let's, okay, when y is equal to 0, 1 and 1/2, we have the roots. And also roots for the first derivative are the same, 0 and 1, 1/2 and 1. Well, we have the first derivative, we have the second derivative, and we also have y. Well, the first derivative, roots of the first derivative are 0 and 1. Y times y minus 1, so it's positive, negative, negative, positive, right? Second derivative, we have all the roots are simple roots, so we have positive, they're all zeros, right? Negative, positive, negative for the second derivative. So that means what? The first derivative, positive, means it's an increasing function. Y is an increasing function. Second derivative is negative, means it's a concave down, right? So increasing and concave down, it looks like this. Increasing plus concave down, right here. So from 0 to 1/2, it's decreasing because derivative is negative, and concave up. So decreasing and concave up, it's like that. From 1/2 to 1, it's still decreasing, but now it's concave down, so it's like this. When y is bigger than 1, it's increasing and concave up, so it's like this. So the solution curve will look like this, basically, but let's sketch this now with all this information. Maybe let's. Okay, so the critical points are like when y is equal to here 0, okay, when y is equal to 1/2, which is here, and when y is equal to 1, we have this, so this x and y. Okay, so what happens here is from when y is bigger than 1, maybe I should take this down a little bit. Okay, when y is greater than 1, we are here, right? This one. It's increasing and concave up, so the curve will look like this. Well, you may have, of course, many curves like this, right? Because solution is not unique, like in the previous example. So basically, we draw several curves like this in the same manner, but it depends on you how many you draw. Let's draw 3 of them, for instance. We have another one, depending on the constants, right? Constants in the solution. So we have 3 curves like this, let's say. You can draw 3, 2 curves, depends on you. When y between 1/2 and 1, well, it's a decreasing function and concave down, so it looks like basically like this. From 0 to 1/2, it's still decreasing, but it becomes concave up, so it's like this. Like this, okay? And again, we draw several lines like this. all right? When y is less than 0, what happens with the solution curve? Well, when y is less than 0, it is increasing and concave down. So it's going to be like this, increasing and concave down. They will look like this curves, okay? So these are the solution curves, basically. Any question with this?
So could have we gotten the same result using the direction field instead?
Yeah, you could do it, but it's hard to guess the precise picture, the solution curves. But if you draw the precise slopes, you will get the same picture for sure. But it's not easy. That's why we follow this way.
Another thing, say we have a very similar picture, but some higher order. Say like instead of y prime, we got y to the prime 4, for example.
That in that case, I mean, depending on the equation, you can still draw it, but you need to know the first derivative, second derivative. If you can derive first derivative and second derivative from the equation, then you can draw it, right? Because this is what we did here. We know the first derivative. Using first derivative, we find a second derivative. But if you know only second derivative, you don't know the first derivative, and you cannot draw the similar picture, okay?
So as long as we can, extrapolate the first and second derivatives from the picture.
Right. That's right. If you can extract second derivative and first derivative from the equation, then you can.
Thanks.
Good. Okay, there is one question, why they are starting minus infinity and go to plus infinity. Well, this follows from the table. So for instance, when y is, look at this part. Look at this part, okay? This is when y is bigger than 1. And when y is bigger than 1, we have this sort of behavior. So y must be bigger than 1. So you must be above the line, the horizontal line here. You must be above this. And it must increase. Increase means from left to right, you go up, okay? Because of this picture here. That's why it goes from like minus infinity to plus infinity. It goes up, okay? So it follows from the table. Well, we draw this horizontal. Okay, there is one question: why do we need these horizontal lines? Without these horizontal lines, it's hard to draw the solution curve. This will help to draw the solution curve, but it's not a part of the solution. Final solution, I would say. You can delete, for instance, the horizontal lines at the end, but they will help to sketch the solution curves, okay? They are not necessary, but without them, it's not easy to draw. Okay, so maybe we have one minute only, so let's go back to the table. There's one question about the table, how we get this table. Well, this table here, we have y prime, y second prime. The first derivative gives us the information about increasing, decreasing. If the first derivative is positive, it's increasing. Otherwise, it is decreasing, right? So the roots of the first derivative, we use this equation. The first derivative. First derivative is 0 when y is 0 and when y is 1. So these are the zeros of the first derivative. They are all single roots. They don't repeat, okay? So that's why we have plus, minus, minus, plus, okay? Between two roots, the sign will change. The second derivative, the roots of the second derivative are here, 0, 1, and 1/2. So they're all the zeros of here, this one, and that one. They are the zeros of the second derivative. So we have plus, minus. At each root, we change the sign. When the second derivative is negative, it is concave down. When it is positive, it is concave up. So depending on this, we have this picture. For instance, this was decreasing and concave up, okay? And using this table, we draw this solution curves. All right. Any other question or comment? Okay, we will stop here. Well, there's one more question. Why do we draw 3? 3 is not important. You can draw 1, 2, 3, 4, 5, as many as you want. Why don't we draw just 1? Because the solution curve is not a unique curve. Remember in the previous example, we had a constant c, right? X squared plus c. That means depending on c, we have infinitely many curves, and we draw several of them to emphasize that the solution is not a unique curve, okay? All right, I will stop here. I will put this recording and lecture notes on OptiClass today. See you next lecture on Friday morning. Bye.
Görüşmek üzere hocam.
Görüşürüz hocam.
Laters.
Bye.